But today I will present a paper that proposes a USB, an implementation for a USB transceiver to help FPGA to FPGA communication, or to make FPGA to FPGA communication. This is the outline. We will talk about the introduction. We will talk about the design details, which is their main design or main thing in this paper. Then the simulation, then the conclusion. The paper started to talk about why USB is important and why it is preferred. One of the advantages, the paper said that it has low power consumption. It talks about some support organizations like USB-IF, which is USB Implementers Forum. Then it said that their design is an improvement for a previously designed paper. The main design for this paper is as can be seen in the picture, the green one. This is the design. We can see that here how the data flows. Data will be initialized in the ROM, then it will flow to the FIFO, to the serial interface engine, then to the physical layer of the USB. And then it will be the opposite way on the receiver side. Why do we need the FIFO? The FIFO is needed because the clock is faster in the FPGA than the USB interface. And the serial interface engine is just to change the data from parallel to serial and make it fit to the USB hardware interface. Then the paper talked about the implementation of the ROM and the FIFO. Since they are basic modules, it just talked about them in high point of view. Here's on the left side, we can see the implementation of the ROM. On the right side, we can see the implementation of the FIFO. The FIFO can be empty and can be full because we sometimes need to write until full, and we need sometimes to read until it's empty. Here is the main thing in this paper, the serial interface engine. It has many subparts, submodules. We will discuss each one of them independently. But the first module is the PID check. The idea of the PID check, it will check the type of the packet will be sent from the FPGA. The packet can be data, can be token, can be head check. There is no implementation for the special packet, which is the fourth type. We can see there are some subtypes for each. So for each type, the total will need 4 bits. That's why in this implementation of the PID check, 8 bits will enter. 4 of them will be the packet type, and the other one will be the negation, so that we know that this is a packet type, not an 8-bit. You can see that this here in the check, the PIDN equal not PIDB here in this module. And then here we can see that it will change the state depending on this type. It will send a signal depending on the type. Here in the CRC design, after we are checking the type of the packet, we will do either CRC5 or CRC16. These are the implementation of the CRC5 and CRC16. Here in this picture, in the paper, I think they made a mistake. The equation is not x to 16, x to 15, x to 2, x to 1. The equation here should be x to 16, x to 12, x to 5, and 1, which is another CRC16 commonly used. Here, the bit stuffing algorithm. We need bit stuffing in this in the USB interface, because if we send multiple ones, because it's used in our non-return to zero inverted. If we send multiple ones, a lot of ones, there will be no change in the in the signal, because 1 means no change and 0 means change. So we need to insert a 0 for after some ones, which is designed as 6. So if we send 6 once, we need a change of data so that the synchronization between the two FPGA will not stop. Then so it will add 0 and then will continue sending once. Here there are error in this design. You can see that if count equals 6, it will output 0, and then it will not reset the counter, which will make it 7 and 8 and 9, which will make the design doesn't work, because here he's checking if counter equals 6, not even higher. So it will just change the signal once, and then it will be sending forever, like the same signal. It will not change it. Also, it is inefficient because we just need. It's inefficient because there are 4 states, which is too much for a design like this. It can be implemented in a lesser way. Here is the bit unstuffing design. The idea here, if we received 6 ones, then we know that the 0 after these 6 ones are inserted by the bit stuffing algorithm. So just we need to say, we need to let the other modules and this system know that the 0, this 0 is invalid. This bit unstuffing algorithm or bit unstuffing design is in the receiver side. So we can't change the data in or data out. We will make them the same, but we will say that this data is valid and this data is invalid, and the out will be the in. That's what should be, what should have been done. But here, a lot of things have been done. I don't know why they make it so much complicated. It is inefficient, as you can see, since what we need is just to check if the data is valid or not. Yes, they want to check if the link is idle or not. So if a lot of invalid data comes, it will change the state to idle, but also it will be less complicated than this. Here, the the non-return to zero inverted encoder and decoder, it is just a mapping. If it's 1, map it to the previous signal. If it's 0, change the signal, the previous signal to the new signal, which is XNOR. If it will be implemented, but it doesn't implement, doesn't say, the paper doesn't say how it implemented it. As for the simulation part, the authors simulate each part independently. I didn't see a simulation for the integrated design. All of the simulations will be in the appendix in this slides. In conclusion, the paper said that their design has less performance than the previous one, but it has lower power consumption, which is one of the main advantages of the USB, so it is a good design. That's the conclusion of this paper. Thank you.